Well, it is my pleasure to speak to all of you today about lift safety devices and to offer as it says on my title slide, a brief history of lift safety devices from roughly 1835 to 1935. In the course of this brief presentation, I will touch on some specific firsts in terms of safety devices and other events associated with lift safety. And this is by no means a comprehensive history of these devices, but will serve, I hope, as a useful outline and remind us of the critical role that safety devices have played in the development of lift technology. Our story begins in 1835 with the lift system known as the Teagle, which was actually developed some 30 years earlier at the very opening of the 19th century and was developed for William Strutt's textile mill in Belper, England. And the Teagle was a very early version of in essence, a sort of traction lift. But for our purposes today, we're focusing on two safety devices that were associated with the Teagle. One was a safety gate that was developed between 1805 and 1835, which ensured that the shaft gate could not be opened unless the lift car was present. What we can take that is not illustrated in these drawings, but what we can look at is a safety stop that was also introduced by 1835, which ensured that if the lift exceeded its upper or lower travel limits, the lift would automatically stop. And we can see that safety in this slide. If you will look, we see the gentleman standing furthest to the right and the shipper rope behind him. If we follow the shipper rope or control rope up just outside of the lift car, we can see an indication of a stop ball, a ball attached to the shipper rope, and we could see the L-shaped bracket that the shipper rope passes through. If the lift car went past its upper limit, the bracket would strike the ship ball, which would then automatically move the shipper rope, stopping the lift and preventing it from crashing into the overhead sheaves. And a similar device was located in the bottom of the lift car. The first patent rather, associated with a safety device dates back to 1854. An American inventor, Daniel Talcott, invented a safety hatch for use in warehouses and other industrial settings. In this schematic patent drawing, we can see that the safety hatches consisted of portions of the floor that would slide out of the way as the lift car approached, and through a series of cams and springs after the lift car had passed, these sections of the floor would slide back in place. We can get a better idea of Talcott's invention, and safety hatches remained in use in warehouses throughout the 19th century by looking at a slightly later version of this device dating from 1868, in which we can clearly see the open lift car and the elements on top and bottom that would push the safety hatch out of the way as the lift car rose and fell through the shaft. This also serves as a reminder that in most warehouses and industrial settings, lift shafts were open. Thus, the need for a safety hatch to prevent unwary workers from falling down the shaft. Of course, this also illustrates another problem given the openness of the shaft. An unwary worker standing on top of one of the safety hatches also put themselves in danger. Also from 1854, moving back to our timeline, we find Elijah Otis demonstrating his ratchet and pawl safety device at the New York Crystal Palace. This event encompasses two firsts. One, this was the first and perhaps only public display of a lift safety device. And also, Otis's invention was the first time a safety device was incorporated into the design of the lift platform. And we could add a sort of first, I suppose, to this story in that it's one of the first missed opportunities, in that although Elijah Otis filed the paperwork to patent his safety device in 1854, the following year he withdrew his application for unknown reasons, and his device went without a patent. That, however, does not mean that we cannot trace the first patent for a ratchet and pawl safety device to the 1850s, because in 1856, English architect Hugh Baines patented a ratchet and pawl safety device. So we have the first patent associated with this particular approach to lift safety. As we can see, comparing this drawing to Otis's drawing, Baines's design was much more complicated, but it embodied the essence of a rack along both sides, and then ratchets that would spring out and catch into the rack, thereby stopping the motion of the lift car should the rope break. In addition to having the first patent, Baines also has the unfortunate distinction of also being involved in the first safety test accident. In 1857, Baines had his safety device installed on a lift in an existing warehouse in Manchester. To demonstrate its effectiveness, he had the lift car raised to the top floor of the warehouse, where Baines and 3 other passengers entered the car, and the lift rope was disengaged. Now, that is the word that was used in describing the accident. We don't know how the lift rope was disengaged or at what point, but the lift rope was disengaged, and the result was that the lift car fell 60 feet and crashed into the bottom of the lift shaft. The safety failed to operate. Now, this failure could have occurred because the lift rope was disengaged such that it still maintained sufficient tension on Baines's safety that the safety failed to operate. Regardless of why it failed to operate, the results were fairly tragic. 2 of the passengers died, the other was severely injured, and Baines himself was also injured with a severe laceration to his foot. This first accident also reminds us of something that we don't know about the history of lift safety devices, and that has to do with how these devices were tested and what were the means of testing, how often were they tested. And as we look through the 19th century, many safety device tests rather occurred in this fashion, attached to existing lifts and then experimented with in buildings that were operational. 1859, American inventor Albert Betterley patented the first air cushion safety device. This was a very, very simple safety in which Betterley applied what he called a parachute type device attached to the bottom of the lift car. At the bottom of the lift well was a receiver or receptacle for the parachute. If the rope broke, the lift car and the lift car fell, when the parachute encountered the well at the bottom, air would be compressed and the air then slowly released around either side of the parachute, thus preventing a serious accident from happening. One of the interesting aspects of this, and it does speak to, although unpatented in the United States at this time, the presence of Otis's ratchet and pawl safety device. Because Betterley, in his rationale for his design, said that his air cushion was needed because of the inefficiency of ratchet and pawl safety devices. He stated, quote, "Their inefficiency in preventing the fall of the car in many cases, as for instance, when some part of the machinery gives way beyond the rope, or where, as may be the case, the rope breaks and is subject to sufficient friction to keep the pawls from falling into the rack until the car acquires such momentum as to destroy the racks and pawls when they act." Thus, Betterley was aware of Otis's safety device and recognized that it also, while effective when it worked, did not always work. Betterley also, in 1859, patented the first interlock door safety device. And the patent drawings illustrate a standard door, as we would find, providing entry into any room. And the upper image shows us the inside of the lift car. When the lift car door was opened, it operated a mechanism that grabbed the shipper rope, which we now see passing through the car, such that the shipper rope could not be moved. Thus, the lift car could not be moved. The use of what we think of as traditional doors that provide access to rooms was typical for many lifts at this time. And the use of sliding doors did not become popular until the 1880s and into the 1890s. One of the other things that these drawings hint at is the presence of a lift car for carrying passengers, although Betterly does not refer to the presence of a car or the design of a car in his patent. That first goes to, again, in 1859, Otis Tufts, who patented his famous vertical railway elevator. Tufts' approach to safety was to abandon the use of ropes, and instead the lift was driven by a massive screw shaft with the lift car rising and falling as the screw shaft rotated. In his design, Tufts included numerous safety devices, including a stop safety at the top of the shaft. Tufts was the first to propose the use of a buffer device at the bottom of the shaft. There was also a speed control employed, but most specifically and explicitly, Tufts provided a design for and an idea for an enclosed passenger car, hinted at in Betterly's design, but explicitly referred to in Tufts' design, recognizing that an enclosed car was necessary to keep passengers safe while the lift car rose and fell through the shaft. Finally, one last event in 1859, we go back to Elijah Otis. In an advertisement for his lifts, Otis used for the first time the phrase improved safety elevator, which very quickly became translated into improved safety lift or safety lift. And from this point on, throughout most of the rest of the 19th century, manufacturers consistently referred to lifts as safety lifts, or in the United States, safety elevators, thereby integrally and firmly linking that concept of safety to vertical transportation. Otis finally patents his ratchet and pawl safety device. The patent is awarded in January of 1861. In February 1861 is one of the first accidents that we know of to an Otis elevator equipped with his ratchet and pawl safety device. The elevator was in a warehouse in New York City. It had recently undergone routine maintenance, which involved replacing the hoisting rope on the lift. The lift was then put back in service, raised to the top of the warehouse, fully loaded with an attendant. And as it began to descend, because the lift rope had not been properly attached to the lift car, it came loose and the lift car fell down the shaft. That action should have caused Otis's safety device to act. However, it did not act until the lift car reached near the bottom of the shaft. And when it, because of the speed of the car, when it attempted to grab hold of the ratchets, as was stated in newspaper accounts, concussion of the safety acting was such that it killed the worker on the lift and injured a worker standing adjacent to the lift opening. When Otis was interviewed about this accident, he stated that the lift car itself had been racked out of place because of intensive use, such that the safety could not operate. But then he also made another statement, stating that he had very specifically, quote, never warranted his elevators to be perfectly safe, as their safety depends in some measure upon their reasonable care and usage by the operator, over whom I have no control. This was the first public statement and acknowledgement from a member of the lift industry that safety was not solely the responsibility of lift manufacturers, but was also a responsibility shared by lift users with regard to ensuring that lifts were not overloaded and that lifts were used safely. And again, an acknowledgement of the complex nature of lift safety. In 1864, we have one of the first overspeed safety devices, in this instance applied on a direct action hydraulic lift, a lift type that we often don't think about with regard to overspeed. What is also interesting about this device, developed by Easton Amos and Sons for a hotel, is that it was intended to be used for both for overspeed in the up direction and in the down direction. We see in the detailed drawing here, we see the cylinder for the hydraulic ram on the far right, and then we have a pendulum type swinging valve, and then we see the inlet and outlet pipe. The pendulum valve was alleged to work such that if the speed of water through the valve exceeded a certain rate, the pendulum would swing, automatically slowing down the flow of water, thus ensuring that the hydraulic elevator, either moving up or down, would not exceed a preset speed. Here we have a detailed drawing showing the valve section on the left, and then its placement at the lower hydraulic cylinder on the right. And then a full drawing of this lift system, which is also another first from 1864. This is one of the first detailed drawings of a lift system published in Europe or in the United States. In 1865, Charles Otis patented the first overspeed safety for a steam-powered lift, and this only concerned overspeed in the down direction. Attached to the winding drum at the top of the shaft was a brake, a band type brake whose action was controlled by a fly ball governor. If the speed of the drum exceeded a preset limit, the action of the governor would cause the brake to act on the winding drum. We can also see in the patent drawing the clear presence of Charles Otis's father's now patented ratchet and pawl safety device. And when Charles Otis introduced this, which he referred to as his improved safety drum, it again was explicitly introduced because of a recognition that his father's ratchet and pawl safety device did not always work as intended, although it remained a feature of Otis elevators through much of the 19th century. This contemporary engraving shows us, or rather gives us perhaps a better idea of how this safety device operated. We see the band brake labeled F in the drawing, and then the presence of the fly ball governor on the left. And its action was very simple and in fact proved very effective. In many ways, it was much more effective and a much more reliable brake system than Elijah Otis's ratchet and pawl safety device. In 1879, American inventor Albert Illiethorpe patented the second air cushion safety device. It operated in a similar fashion to Betterly's earlier design from 1859, although now the parachute is missing. Betterly simply designed the bottom of the lift platform such that it traveled very, very close to the shaft walls, and as the shaft neared the bottom, the walls tapered slightly, so that if the lift car fell, it would compress the air and the air would slowly leak out, so to speak, around the bottom of the lift car. Illiethorpe added in a few additional features. One was an air valve, as he called it, at the lower portion of the lift shaft, which we can see in section on the left, and then in elevation on the right. The air valve operated such that as the lift car rose, air was allowed to enter into the shaft. When the lift car descended, the compressive action of the air caused the lift valve to close. Illiethorpe also, as part of his design, insisted on the use of sliding doors to access the lift shaft and the car, because he felt sliding doors provided a more airtight environment for his safety to operate. This was one of the first overt references to the preference for sliding doors as opposed to normative hinged doors as were used on typical rooms. I included this safety from 1888 by Adolphe Gallinat in this talk because it's representative of any number of rather eccentric devices that were developed and associated with ensuring lift safety. The inventor in this case had no connection to the vertical transportation industry, but he was in good company with many, many others who proposed idiosyncratic solutions for lift safety. But it does serve us as a reminder of how firmly the concept of lift safety and of its importance was embedded with the public. This design consisted of a large fan placed at the top of the shaft, with fan blades designed such that, and we'll look at a detail, they were hinged. As the lift car would rise, the fan blades would collapse. When the lift car descended, the fan blades opened and the degree to which they opened was controlled by a chain. We can see the chain illustrated here. I could also slide the fan blades along the bar they were attached to, and thereby, in theory, this would automatically ensure that the lift car could never exceed a preset speed. A more normative safety, clearly coming from the lift industry, was Charles Pratt's undercar overspeed safety device, one of the first devices proposed to be placed under the car from 1857. The design of this safety was made possible by the development of modern steel guide rails, and we can see those indicated in both the elevation and then the plan view looking up at the bottom of the lift car that we see in the lower image. The presence of steel guide rails allowed Pratt to design a system whereby a clamping type system could be used, again, whose action was controlled by a flyball governor that was linked by a series of cables. Thus, if the car exceeded a certain speed, then the safety would act. The first in-car communication system as a safety device dates from 1889. In this instance, and I apologize, I do not have a photograph of this installed in the Park Row building, but it was the first building to utilize telephones as an in-car communication system, and the phones were directly linked to the building engineer, so that if the lift operator experienced a problem, they could immediately call the engineer, report the problem, and then it could be resolved. It takes a long time before in-car communication systems are required safety features for lifts. But by 1889, there's a recognition that the new technology represented by the telephone had a place in lift safety. One of the critical problems with lift safety that was experienced throughout the 19th century and into the early 20th century was the fact that there were no automatic leveling devices. And it was up to the skill of individual lift operators to stop the lift car level with a landing. In many instances, if the lift car was within 1/2 inch of level, that was considered a safe landing. But it still presented, obviously, a tripping hazard moving in or out of the lift car. This represents, by George Hale, we see a series of lights here, one of many safeties that were developed around lift thresholds. In this device, there were various systems whereby when the lift car stopped, a light would automatically shine onto the threshold, highlighting whether the car was perfectly level, and thereby providing a visual cue to passengers entering and exiting lift cars, ensuring safety. Automatic leveling systems were developed between 1900 and 1915, and by 1920 were common features of lift cars. It takes 15 or more years to develop these systems because of the challenges of both first developing a system to ensure that as the lift car approached the landing, it would slow to an appropriate speed. And then once we'd achieved a slower speed, ensuring that the car both stopped level with the landing, and if for any reason it went past the landing, it would automatically return to the landing and stop at a level point. Paralleling the development of automatic leveling systems and going back to the introduction of sliding doors in the 1870s, by the early 20th century, we have automatic sliding doors that begin to be introduced. And as soon as automatic sliding doors are introduced and their action was governed by when a lift car stopped and when the operator began movement of the car, there was an immediate recognition that they presented a rather serious safety problem, in that passengers were becoming caught by the moving sliding lift doors. The first door reversal safety system was developed by two Westinghouse engineers, Luther Kennard and James Dunlop, and patented in 1931. It consisted of employing what at that point in time was sometimes referred to as an electric eye or a light beam with a photoreceptor, such that if a passenger, this is now a very common safety feature to us today, if a passenger broke the beam of light, the door would immediately reverse its action and would remain open. Westinghouse marketed this system as their safety ray. And here we can see an advertisement from the early 1930s, and we can see the beams of light. Two beams of light were employed, one striking the passenger exiting the car at the knee level, the other striking the passenger just above his hand. And this proved to be a very effective safety system, and as we know, with contemporary lifts, has developed to a very high degree. I hope that this very brief talk has illustrated both the development of these safety systems, and in this outline is highlighted several things that we know in terms of development of safety, but also many things that we still don't know and I believe are worth exploring. One of them I've already mentioned, the development of lift safety devices and testing. The first lift safety towers date from the very end of the 19th and early 20th century, but even then we don't know with lift test towers how they were employed, what kinds of tests were done, how many times tests occurred, and in many instances what appears to have happened is devices were invented and then simply placed on the market, and the market served as the testing site. There's more work that needs to be done on the history of testing of safeties. And also, there are many, many safety devices that were not included in this talk that also deserve further attention, as well as the fact that this talk looked at patents, the patents record primarily in the United States, touched on the patent record, in England. There's also the patent record, of course, in Europe, which needs further investigation. It's been my pleasure to have an opportunity to present this, and I thank you very much for your time.